Hi everyone, welcome back to Geeks for Geeks practice and welcome back to the Microsoft in 29 days self-paced course. So just a quick reminder, in case if you have not registered yourself for the Microsoft in 29 days self-paced course, so you can make sure to register yourself for this course by clicking on the link that is given in the description of this video. After you register, so again if you click on the start button, so you will get access to all the recordings of the various days that are there in the Microsoft series. And apart from this, you will also get access to the leaderboard where you can check your progress amongst your peers. So for every day, you will get the 2 recordings that are available. And apart from this, you will get to practice 5 problems for every day. 2 problems that we do as classwork and other 3 problems that I give as homework. Now today's lecture will be important because we'll be discussing Huffman encoding, which is a very important concept. Apart from this, we'll also be discussing the other problems, that is merging k-sorted arrays, and it is also important for merging k-sorted linked list. So now let us move to the problems. So the first problem that we are going to discuss is Huffman encoding. So the problem says that we have been given a string S which consists of distinct characters of size n. So the string is of size n and it consists of distinct characters, and the characters has correspondingly frequencies. Okay, so we have been given the characters and we have been also given their frequencies. So the characters are given in the string S and the frequencies accordingly respectively are given in the array F. So the problem says that our task is to build the Huffman tree and print the Huffman codes in pre-order traversal. So we have to note that while merging, if 2 nodes have the same value, then the node which occurs at first will be taken on the left and of the binary tree and the other one on the right. Otherwise, the node with the less value will be taken on the left subtree and other one on the right. So we'll discuss these things in detail. Now let us move to the example. So first of all, what is Huffman encoding? The first question will be that, okay, what is Huffman Huffman coding? So if I tell you that, suppose I give you some words, suppose that I give you words, like suppose I give you characters, suppose I give you A is suppose having the frequency as 50, suppose B has the frequency as 10, suppose C has the frequency as 30, suppose D is there, D has the frequency suppose as 5, suppose E has the frequency as 3 and F has the frequency as 2. Okay, if I ask you to represent these characters, so you can say that if we have to represent ABC in terms of ASCII, because we'll be sending them as messages, so if we have to represent them in terms of zeros and ones, so we can represent them in some form of 7-bit integers, right? Because if we see, so we have total 128 characters, that is nothing but from starting from 0 till 127. So we can do what? We can use 7 bits, right? We can use 7 bits to represent A, B, C, D individually, right? For A, we can use 7 bits, okay? For B, we can use 7 bits. For C, similarly for D, E, F. So for A, if I am using 7 bits, okay? If I'm using 7 bits, suppose that the total number of characters that I have, like total sum that I have is 100, okay? Like 50, 60, 35, 3, 2. So total sum is 100, okay? So in that case, for one character, I'm taking how much? 7 bits. So can I say that for 100 characters, I'll take nothing but 700 bits, okay? So if for one character, I'm taking 7 bits, so for 100 characters, I'll simply take 700 bits, which is quite a lot. So can I reduce it? Yes, I can reduce it. So instead of doing this, what I could have, what I could do is, I could say that instead of representing using 3 bits, I can do like using 7 bits, what I can do is, I can represent them using 3 bits. How? So if I see A, so A I can represent like let's say 000, okay? B I can represent as let's say 001. Let's say I represent C as 010. Let's say I represent D as something like 0, 1 and 1. Okay, up till now we haven't started the Huffman. We are just discussing how we can return, like how we can store the data, right? So E I can represent as what? Like we can represent E as let's say 100, and let's say we can represent F as 101. So here you can see that by using just 3 different 3-bit positions, like by just using 3 bits for a particular number, I'm able to represent all these 6 characters that are there, right, differently. So I can say that if I have to talk about this thing, so how much space I'm taking. So now for every character I'm taking 3 bits. So if there are 100 characters, so I will take how many bits? I'll take like 3 into 100, that is nothing but 300 bits, which is quite a lot, which is again quite a lot. So can I reduce it? Yes. Now what I can do is I can apply the Huffman algorithm. Okay, Huffman, which is a greedy algorithm. So what I can do here is, if I've been given these characters, so I will, like, Huffman will help me to decide that, okay, how do I actually represent the each of the characters. Okay, so what I will be doing here is, if I've been given the characters and the frequency, so I'll simply insert all these characters along with their frequency. Okay, like I'll insert all the frequencies in, let's say, a min heap. Okay, so I'll make use of a min heap and I'll insert all of them. Now what I will do is, like, how does the Huffman algorithm work? This will also be taken into care. So Huffman algorithm works by taking two of the most smallest frequencies. So I can see that the smallest frequency is 2, that is f is equal to 2, f is occurring 2 times, and the second smallest frequency is e is equal to 3. So what I will do is, I'll take these two frequencies out, and first of all, like, I have to build a Huffman tree. So basically every node initially will behave like a leaf node. So what I will do is, I'll first of all have a f. Okay, I'll have f. Now if I see f is occurring 2 times. So if the character is having lesser frequencies, I'm indicating it on the left as mentioned in the question. Then if I'm having e, so e has a frequency of 3. Okay, now I'll pop these two out of the priority queue. Okay, after this what I will do is, I will insert, instead of these, I will merge them, right? I'll merge these two. And what is the size now? What is the size of the new node? The size of the new node is nothing but 5. Okay, so I can say that, let's say this is node number 1. Okay, let's say this is node 1 and its size is what? 5. Now I'll insert it into the priority queue. What will happen now is, like, I can see that basically I'll make a new node and whose left child will be nothing but f and right child will be nothing but e. So I'll develop this relationship as well. I'll develop this particular pointers as well. Okay, so every node, every node will behave like node of a tree, which will have a left and the right. Okay, now what are the next two smaller elements? So I can see that node 1 is equal to 5 and d is equal to 5 are the ones. So what I will do is, I'll place a d here. Okay, this is nothing but node 1, so I'll have a d here, and what I will do is, d has a frequency of 5, so I'll combine these two up. So when I combine these two up, so what do I get? I get a value as 10. So I'll erase these two data from the priority queue, that is the min heap. And now what will happen here is, min heap will help me to retrieve always the minimum element from the top. Okay, one by one. So now I will say that, okay, node 2 is there, that is having the frequency as 10. Now what will happen? Again, I can see that what are the two minimum elements. So b is equal to 10 and node 2 is equal to 10. So that these are the two ones. Like, so I will do what? I will insert a d here. Like I will have a b here. Let's say b is standing here. And what I will do is, now I'll merge b and the node number 2. So b is having the frequency as 10. If I merge these two, so the frequency becomes nothing but 20. Okay, the frequency will get updated to 20. After this is done, after this part is done, so what shall we do? Now we can say that, okay, we'll remove this particular node as well and we'll remove b. So now what is the node? So the node 3 that I've inserted, that is the combined node, is now having the frequency as, let's say, 20. So what I should do now? So I should again take the two minimum. So first of all, I'll take out 20, then I'll take out c is equal to 30. So 20 is there and 30 is there. If the higher value is there, so I'm inserting it at the right side. So I can say that c is there. Okay, c is there, and c is having the frequency as nothing but 30. So I'll combine these two up. When I combine these two, so what do I get? I'll get nothing but the value is 50. So the combined value that I'm getting is 50. So I'll insert 50 inside. And I'll keep on building this left and right child relationship every time. So now the node, let's say 4 that I've built again is having the frequency as 50. So I'll take two elements out again. So you can also notice one thing, that I can do this operation if the queue has two or more elements. If the queue doesn't, like if the min heap has two or more elements, then I can perform these operations. Otherwise, if it just has one element, then the operations would stop. So I'll have a here. I'll have a here. Okay, and then a has the frequency as 50. Okay, so again if I combine these two, so I get the node as 100. Okay, I'll get the node with the value as 100, and this indicates that total number of characters that I took was 100. So now I'll insert 100 into the priority queue. The node 5, let's say, with the value as 100. Okay, now there is just one element, so that means the traversal, like the priority queue work is done, because I can see that now the Huffman tree has got built. And as mentioned, what I will do is, like, I will do what? I will mark the left side as 0. Okay, I'll mark the left child as 0. Every left edge that is going from a particular node, I'll mark it as 0. And I'll mark the right edge as 1. So 0, 1, 0, 1, 0, 1, 0, and 1. Okay, once I've done this, so how do I represent the numbers? How do I actually get them? So if you will observe clearly, so A is equal to what? A is equal to, if I have to build A, so I'll traverse this edge. So A is equal to 0, right? Basically, you will observe this. I'll get this using the pre-order traversal, basically, or any traversal, like that depends on the question. So if B is there, so if I have to see B, so for B, 1, like I have to traverse this edge, right? Basically this edge, 1, 0, and 0. Okay, so that is how I'll get B. So let us quickly get B as well. So B is nothing but 1, 0, 0. So I'll quickly build for B as well. So B is nothing but, B can be represented as nothing but 1, 0, and then 0. If I look for C, so C can be represented here. C is standing here. C is standing here. Okay, so C is represented as 1 and 1. Okay, if I look for D, so D can be represented as 0, 1, like basically following this part, 0, like 1, 0, 1, 0. Okay, after this, if I look for E, this is nothing but the Huffman tree. This is the complete Hofmann algorithm. After this, what we will do is we will have E. So E can be represented like what? E is standing here down. So you will see E is what? Like 0. Like no, first of all, if I have to go to the left side, so that would be nothing but 1. Okay, 0, then 1, 1, 1. Okay, you can observe like 1, 0, then triple 1. And after that, if I have to reach F, so F is what? If I see from the starting, so 1, 0, 1, 1, and 0. So 1, 0, 1, 1, and 0 is how I'll represent F. Now you'll observe one thing, that how many bits is A taking? A is taking 1 bit. Okay, D is taking 3 bits, C is taking 2 bits, D is taking 4 bits, E is taking 5 bits, and F is taking 5 bits to represent. Now, which was the, if you remember, which was the character which was having the highest frequency? I can say that A was having the highest frequency because A's frequency was 50. So that means A had 50. So I can say that the character that was occurring most number of times is given the least number of bits. Okay, this is the greedy algorithm. And if you see F, so F was occurring how many times? F was just occurring 2 times. So that means F is the character which is occurring least number of times is given the most number of bits. Okay, so if the character that is occurring most number of times, it is given, if it is given lesser bit, so it will take lesser space. Okay, if the character like similar, like if I keep on doing this, so characters which are occurring a higher number of times, they are represented with lesser number of bits. And if this part is done, so this ensures that the bits taken are less, because if the characters, if A is occurring 50 times, and if I'll give a higher bit, if I'll give it a higher bit representation, it will take a lot of space. Otherwise, if A is occurring more number of times, so I'll give it lesser bits. If I give it lesser bits, so that means it takes lesser space, and I can give the larger bits to the elements which are occurring very, very less number of times. In that case, I'll save a lot of bits. Let's see. So 1 into 50, 2 was occurring how many times? 2 was occurring 10 times. You can see in from the diagram. C was occurring how many times? C was occurring 30 times. So I have given it, you can see lesser bits. D was occurring how many times? D was occurring 5 times. Okay. E was occurring how many times? E was occurring, I think E was occurring from the diagram, we can see it was occurring 3 times. So if I take out the total sum of the bits that I have taken, so that would come out to be nothing but, I think, 185. You can see that, like this would be 50. 50 plus 30 would be nothing but 80. Okay. 80 plus 60, 80 plus, we can say this thing, 80 plus something like, let's say 60 would be nothing but 140. Then this is 20, this is 15, and this is 10. So overall it is what? This part is 20 plus 15 plus 10. That comes out to be 45. So 140 plus 45 overall comes out to be 185. So now how many bits I'm taking? I'm taking just 185 bits. Okay, 185 bits. Earlier when I started, so I thought that okay, let's do it in 100 bits, 700 bits. Then I took how many bits? After that I took 300 bits. If I give 3 bits each. But if I do it optimally using the Hofmann algorithm, so I can do it using just 185 bits. So this is the Hofmann algorithm. It is an algorithm which is greedy in nature, and it helps us to represent every number in some different bits, such that the character or the data which is occurring most number of times, it is given the lesser bit, and the character which is occurring the most number or like lesser number of times, it is giving more bits, so that the overall bit that I take reduces down. Okay, that is what the overall concept for this Huffman coding is. And for this implementation, I use, since this is greedy, so I always try to minimize. So I'll use the min heap for this particular algorithm. Okay, now let us try and see the code implementation for it. And how many nodes are there? So total n nodes are there. So that is why if you will talk about the time complexity, so it will be nothing but order of n log n only. Okay, it will be nothing but order of n log n, because if I'm using priority queue, so for one time the like Heapify process takes log n, so there are n different nodes, so it will take n log n time. Okay, so now we'll do the traversal for this and see how we are doing. So you can observe that when I'm going to the left child, so the edge will be considered as 0. If I'm going to the right child, so edge will be considered as 1. So let us try and look at the code for this particular approach. So what I've done here is, if you will observe, so first of all I have declared a priority queue, that is nothing but the min heap. Okay, which will consist of the nodes, and it has a vector to it and the comparator function. Okay, this is the min heap that I've declared. Every single node, every leaf node I have inserted into the priority queue first of all. Okay, along with its data it is built. After that, what I've done is, if the priority queue, if the min heap is having size greater or equal to 2, then I have first of all taken out the left child, that is the minimum, then I have popped it out, then I have taken the right child, which is the again the Heapify process will take place, so the new top element will be again the minimum element of the min heap. Then I have made a parent node out of it, that will consist of the left node data plus the right node data, as I was doing. Then that for that particular parent that I have developed, that is having the sum, that its left would be nothing but the left child. Okay, so its left would be pointing to the left child and right would be pointing to the right child. So this is how I'm building the nodes one by one. Then I'll push this particular node into this particular parent node into the min heap. And once this is done for all the nodes, so this is nothing but the process that we have discussed. So this will help me to build the Huffman tree. Once the Huffman tree is built, so you can observe one thing, that this node with the value 100 will be contained in the priority queue, and that is nothing but my root node of the tree. So I'll store it in the root. Okay, the priority queue top will now consist of the root, and I'll pop it out from the priority queue or the min heap. After that, I'll have a vector string answers, and I'll do a pre-order traversal on this particular tree whose root I know. Okay, and how will I do a pre-order traversal? As you can easily observe, so if the root is null, I will simply return. But if the roots left and the right child is not existing, right? If the roots left is null, okay, and the roots right is null, so in that case I'll simply insert the current string into the answer, because that means I've built it. Okay, if suppose that whenever I reach the leaves, right, you can see here, whenever I hit the leaf nodes, so that means I have built the string, so I'll simply do that. Otherwise, I'll call the pre-order traversal, and I'll call for the left guy, and if I'm going to the left child, so the edge will be added as 0. Okay, so s plus 0 comma answer I'll be passing, and if I'm going to the right child, so I'll pass right comma s plus 1 comma the answer. Okay, this is what I'm doing. So this is something but the implementation and the dry run for the Hofmann algorithm. So I hope that you understood this particular explanation. In case if you did, so make sure to hit the like button and comment down understood as well. Thank you for watching this video. In this video, we will discuss the problem merge k-sorted arrays. The problem says that given k-sorted arrays arranged in the form of a matrix which is of size k cross k, the task is to merge them into one single sorted array. So let us quickly take the sample example to understand things better. So if we look at the sample examples here, so in the sample example, we can see that k value has been given as 3 and the array has been given 2D arrays like 1 to 3, then we have been given 4, 5, 6 here, and then we have been given what, 7, then 8 and then 9. So we can easily observe that there are k arrays given to us, right? K sorted arrays, like this is the first array, this is the second array, this is the third array, and you can see this array is sorted, the array 4, 5, 6 is sorted, 7, 8, 9 is sorted. So basically we have been given k arrays where the k value is here 3. We have been given 3 different arrays which are sorted, and we are given this data in form of a 2D structure. So now what we need to do here is we need to merge this. So in this, the answer is very generic, like we can see 1, 2, 3, 4, 5, 6, 7, 8, 9. It is not necessary that it will be like that. It could also have been like 1, 2, 5. Then let's say it could have been something like 3, 4 and 6, and then 7, 8 and 9. Or they could have been more jumbled, but every array in itself would have been still sorted. So how can we do this particular question? So maybe what we could have done is we could have inserted all the elements of the matrix into an array, and then we would have simply sorted the array such that we could have got the final answer. Or another approach that we could have done is we could have basically inserted all these elements into a priority queue, or we can say into a min heap. And once we have inserted all the elements into a min heap, so you can take the elements one by one out and then get them into an answer vector, right? This is what we could have done, but there is a better approach for it. So what we can do here is we can understand, let's say if the data is given some more in random fashion. So if suppose that instead of this we were given here, let's say we were given 5, here we were given 3, here we were given 4, here we were given, let's say, 8, and apart from this, let me check. So 1 2 3 4 5, and then let's say 6 was there, 7 was there, 8 is there, and 9 is here. Okay, so these are the values that I would have been given. So we can do it using the heaps only, that is the priority queue or the min heap. And what we can do is we can do it in efficient and space optimized manner, because if we do it normally, so it will take using the priority queues. So if we insert k square elements inside, like total number of elements are k square, so for doing this it would take k square log of k squared time complexity, because total number of elements are k square, and log k square also, because if there are n elements, so n log n is the time taken in the priority queue. Okay, and the space complexity could have been order of k square if we insert all the elements into the priority queue. So we can better optimize the space in this case. What we can do here is we can say that we'll insert the first element of the every row. For each row that is there, this is the 0th row, correct? This is the first row, this is the second row. So for each and every row, we will do what? We will simply insert the first element of it, right? We'll simply insert the first element of it into the priority queue along with the row number. So we have the row 1, 0, 1 and 2. Okay, so basically from starting from 0 to k minus 1, that will be the row numbers. What we will do is, like, let's say if I insert 1, okay, into the priority queue, if I insert 1, then I insert 3, then I insert 6. So I insert first element of each and every row. Okay, then I'll build an answer vector and I'll take out the minimum. So minimum is 1, then I'll take it out. Then after that, I should replace it with which element? I should replace it with 2 basically. Okay, but how do I replace it directly? Because if I'm just swapping out 1, so I do not have any other information with it. So because I do not have any other information, so what I will do is, if I'm storing, so while storing the numbers in the first part of the pair, either I can build this pair customizedly, or I can use the help of, I can make the help use of pair int comma int in C++. In other languages, I can build a class for this. So I will have what? I will store the element along with the row to which it belongs. Okay, so I will say that, okay, 1 belongs to the row 0, then 3 belongs to the row 1, and 6 belongs to the second row. Okay, because 0th row, first row and second row according to the 0 based indexing. After that, like, basically the priority queue will do the sorting or the management of the element. The min heap that is there, it will do the management of the elements according to the first parameter. So if the first element is if the first part is smaller, so according to that the sorting will be done in the priority queue. So the minimum element which will have minimum first parameter, that will be at the top. So 1 is at the top, I'll remove it out. Okay, but how do I get access to this element? Because I need to get access to this. Then let's suppose I pop out 2 after pushing it into the answer, so I need to get access to this 5. So for that, what I will do is, for each and every row I will have pointers, right? So I'll have a ptr array which will be of size k. So ptr of 0 will be there, ptr of 1 will be there, okay, and ptr of 2 will be there. These will be the pointers. Initially they will be pointing to the first element, okay, that is the 0th index. After this, once I've taken that out, so I'll increase the pointer by 1. So pointer increases by 1, so pointer ptr of 0 becomes 1. After that, we point to this particular element, and then what I can observe is, I can simply observe this part, that I will insert this 2 with the row. After this, again 2 is the smallest element, so I'll take out 2, and then once I take it out, so again I need to increase the pointer because I'll move to the next element. So pointer moves to 2, and then it will point to this element 5. Okay, so I will insert in the priority queue or the min heap, I'll insert simply 5 comma 0. After this, the minimum element now is nothing but 3, so I'll take it out. So I'll take 3 out, and the row it belongs to is the first row, like the according to the 1 based index, 0 based indexing. So that's why I'll increase the pointer of it by 1, and then now it points to 4. So 4 comma 1 is inserted. After that, I can see after the heapification process, 4 is the minimum element, so 4 will come out of the priority queue or the min heap, and then the pointer will start pointing to the third element, that is nothing but the 2 in the first row. So that is here. Now what will happen? 8 comma 1 will be inserted. Now we can see here that what is the minimum element. So minimum element is nothing but 5. So I'll take 5 out. I'll simply insert it here. Let's say I'll insert it in the answer, and then I'll increase the pointer. So pointer increases to 3. Now you can see that pointer is pointing outside because the pointer, the maximum that the pointer of a particular row can go is lesser than k. It cannot be equal to k, because if it's equal to k, so that means that the array has got exhausted for that particular row. So I'll not insert any further from that particular row. After that, what I will do is, so I need to keep a check on this. Now my element is, which element is lesser? So 6 is lesser. So I'll take out 6, I'll print it, and I'll increase the pointer by 1. So pointer increases to 1 and then I'll insert what? We'll go to 7, because the pointer points to the second in the row number, like row 2, it will increase. So I'm pointing to 7 with row as 2. Then 7 is the minimum, so I'll take it out. Pointer increases to 2 and 7 is taken out. After that, it points to what? 9. So pointer increases to 2 and 9 comma 2 is inserted. After that, 8 is taken out of the priority queue. Then 8 is taken out. After that, after 8 is taken out, so simply what will happen? We will simply increase the pointer. So pointer changes to 3. That means no other element can be inserted, because I have exhausted this particular row 1 as well. After that, what I will do is pointer 2. So take out 9 and 2, like 9 comma 2. So that means 9 is the next minimum element. After that, move the pointer. So pointer changes to 3 and I point at the end. So what happens here? When I point at the end, so that means I have exhausted. Now the moment the priority queue becomes empty, so I can simply terminate. So for doing this, if I will observe here clearly, so the space complexity is what? At one point of time, I'm not storing more than k elements. So the space complexity for this approach will be order of k, whereas the time complexity will be the same, that is nothing but order of k square log k. Why k square? Because we are having processing total number of elements, that is k square, and log k because the heapify process takes logarithmic of size of the priority queue, like size of the min heap time. So logarithmic, like size of the priority queue will be k at most. So k square into log k is the time complexity. Let us try and implement this code and see what happens. So what I will be doing is, I'll be given this particular function. So first of all, I'll declare the answer, okay, vector int answer. Then I also need a pointer array, so I can declare the pointer array for k. Initially all the k nodes would point to 0. Then I also need a priority queue, so I'll declare it, that is a min heap, and it will be of pair int comma vector of pair int comma greater pair of int comma int. So this is how I'm declaring a min heap. After I declare the min heap, so this is how I'll declare it, like then I'll say pq, and then I'll insert I'll insert first of all the starting elements. So for every row I'll insert the first element. So I'll insert, I'll iterate for each and every row. I start from 0 is less than k I plus plus, and then we'll say that pq dot push in the priority queue will push what? Simply the array of I0 for the every ith row. I'll insert its first element into the priority queue along with the row. So the row currently is I. After this part is done, so what we will do is we'll simply iterate. So while the priority queue size is greater than 0, till that point of time we'll keep on iterating. And what we will be doing here is, we will simply first of all take out the top element. So we can say that it will be in form of a pair. So we'll say that pair of int comma int, let's say p is equal to priority queue dot top. So I'll take out the top element and then I can pop it out simply. I can pop the top element out, and once I've done this, so inside my answer, what I will push back is, inside my answer I'll simply push back nothing but the p dot first, because p dot first will actually consist of the element. So I'll push it, and then I need to find which row to it's belong to. So this element belongs to the row. The row is stored in the second part of the pair. So p dot second, if I do p dot second, so this in the second part of the pair the row was stored. So what I will do is I'll increment the pointer for this particular row by 1. So I'll say that pointer of row plus plus, and I will check that if the pointer of this particular row, okay, if it is lesser than k, if it is lesser than k, that means more elements are there inside this row that I can insert. So I'll insert this particular element inside my queue. So inside my priority queue, so I'll simply do priority queue dot push array of the row, okay, and ptr of row. So this particular pointer, wherever it's pointing, I'll simply push it, and then I'll push the row as well along with it. After this is done, so you can simply pop it out. And once this process has been done for each and every value, so if it is if the pointer exceeds the k value, in the, like the all the elements are exhausted for a particular row, then I'll not be inserting it back again. And then in the end, I think I can simply return the answer here. So let us quickly try and compile this to see if it works on the samples or not. Okay, so we are getting some errors here. It says pointer of k, yeah, so I should declare it as small k. Other than this, it says that pointer was not declared. I think now there should be no issue about it. It seems to work on the samples. Let us quickly try and submit this code. So you can see that our solution was able to pass all the test cases. In case if you understood this explanation, so make sure to comment on understood and hit the like button. Thank you.